Hello, my name is Francis Tully, and today I'll be going over my presentation on the research that we conducted. The title for today's presentation is Antarctic SuperDARN Observation of Medium Scale Traveling Ionospheric Disturbances. Medium scale traveling ionospheric disturbances, or in short MSTIDs, are irregularities that occur in the Earth's F region in the ionosphere. They're usually associated with atmospheric gravity waves, and they usually have periods of between 15 to 60 minutes with horizontal velocities of between 100 to 250 meters a second. And also they have horizontal wavelength of a few 100,000 kilometers. Studies conducted of MSTIDs using the SuperDARN Auroral radar network, or in short SuperDARN, in the Northern Hemisphere have shown some strong connections between the polar vortex and MSTIDs. Uh, Polar vortex is a region in the Earth where there's low pressure and very cold air. And studies conducted of MSTIDs in the Southern Hemisphere using the Franklin Island SuperDARN radar have also shown some strong connection between MSTIDs and both solar wind magnetospheric coupling and lower neutral atmospheric wings. The source of MSTIDs in the southern atmosphere is still ambiguous. We still don't currently know precisely what is the cause of MSTIDs in the southern hemisphere. We conducted a study looking at the MSTIDs of the McMurdo Station and discovered that what we were looking at, the TIDs that we were analyzing, were actually, in fact, polar cap patches and not MSTIDs. Polar cap patches are enhanced plasma. A brief explanation of what the SuperDARN network is. The SuperDARN network is a high frequency radar that can be found in both in the northern and southern hemisphere. They used to study both mid and high latitude ionospheric irregularities. As you can see right here, we have radars in the northern, a lot of radars in the northern hemisphere and in the southern hemisphere. There have been more studies conducted in the northern hemisphere. That's why there are more radars in the northern hemisphere in comparison to the southern hemisphere. Um, the radars with the blue field of views are the high latitude radars, and the ones with the red field of view are the mid latitude, and the green ones are the polar cap. The SuperDARN is used to study backscatter, which is classified as either ionospheric scatter, or example half up, and or ground scatter, example single hop. The SuperDARN MSTID are usually seen in ground scatter because of the focusing and defocusing of arrays caused by MSTIDs. Ionospheric scatter is also usually represented using slant range, whereas ground scatter is usually mapped onto the ionospheric reflection point formula by Bristol. As you can see right here, we have a formula RE, which represents the Earth's radius and times inverse of sine. And inside this inverse of sine, we have a square root of r to the second power divided by 4 minus h squared. R right here represent the range to the scattering point on the ground, and the h right here represents the reflection height. The two images down below here, right here represent the backscatters, ionospheric scatter right here. We have a radar right here, and a beam is sent to the Earth's ionosphere and get reflected in Earth's ionosphere and back to the radar. That is known as ionospheric scatter, or we can view as a half hop. And right here on the right-hand side, this image right here is the ground scatter. We have a radar located about right here, sends out a beam ray. and the ionosphere reflects it back to the ground and back to the radar. There's actually a reflection point right here and on the ground, but when dealing with ground scatter, we mostly focus on the reflection point in the ionosphere. Now, on a quick, a brief example of MSTID signatures to show how MSTID should actually look like is displayed right here by the string time plot. As you can see, the velocity of the MSTID should always be negative. That correlates with MSTIDs associated with atmospheric gravity waves. Now, our study using the McMurdo Station revealed to us that the TIDs that we were observing were in fact not MSTID. We're not MSTIDs. We look at the MSTIDs in Antarctic Station, particularly the McMurdo Station. We conducted our analysis looking at the power and the velocity range time plots along beam 7 of the McMurdo Station. We looked at particularly the 2017 data. We looked at the whole year and try to analyze all the data that we had for the McMurdo Station. After our analysis, we compare our data with the Blackstone radar, which is from the Northern Hemisphere, and observation revealed to us that there's more ground scatter in the Blackstone radar, because the Blackstone radar had its field of view is primarily over ground, whereas the McMurdo Station had a field of view that was primarily over ice. And our results actually supports that. Right here down below in the table, we have the Blackstone, the number of ground scatter from the Blackstone radar. We have 7.8 times 10 to the 7 number of ground scatter, and overall scatter of 10.9 times 10 to the 7. And the percentage of ground scatter that we had in the Blackstone radar was 71.6%. And for the McMurdo Station, we had a 7.2 times 10 to the 6 number of ground scatter, and overall scatter of 58.5 times 10 to the 6, with 12% of ground scatter. As you can see, when you compare the number of scatter in the Blackstone is much more than the number of ground scatter in the McMurdo Station. This was due to the fact that the McMurdo Station field of view was primarily over ice in comparison to the Blackstone, which had a field of view that was primarily over ground. Even though not a whole lot of ground scatter was observed in the even though not a whole lot of ionospheric scatter was observed in the McMurdo Station, we did find some TIDs that look like MSTIDs, but with meticulous analysis, our results suggested that what we were actually observing were in fact polar cap patches and not MSTIDs associated with atmospheric gravity waves. Right here is one of the results that we attained, rain time plots right here. As you can see, there's a change in direction from towards the radar before 1200 universal time to away from the radar after 1200 universal time as the radar rotates under the polar cap patch. There's a change in velocity. Usually MSTID is associated with atmospheric gravity waves. Actually, not usually, all the time. The velocity of MSTID is associated with atmospheric gravity waves always have negative slope. But right here, as you can see, the velocity changes in direction from negative to positive. This led us to believe that what we were observing was in fact polar cap patches and not MSTIDs. Out of the 13 days that we examined, the average velocity of the polar cap patches was 562 meters a second, and the standard deviation that we attained was 358 meters a second. Our objective was that we set out to find out the source of MSTIDs associated with atmospheric gravity waves. But what we discovered was in fact that what we were observing was in fact polar cap patches and not MSTIDs. For future work, we plan on looking at the autorators in the Southern Hemisphere and conduct a thorough analysis on that data. We plan on looking for MSTIDs associated with atmospheric gravity waves. And we also plan on comparing our results with the results from the Northern Hemisphere. And we also we hope to find out the source of MSTIDs in the Southern Hemisphere. And that concludes my presentation for today. Any questions, Veronica?
No, I don't have any questions.
And congrats